Some of the largest stars in the universe are also some of the strangest. Conventional science would have us believe that these stars are near the end of their life, and yet they show some features that we also find in young stars. They claim that these stars will expel vast amounts of material, which will eventually form a planetary nebula. And now they have discovered a star which is not only ejecting material in this manner, but also an expanding ring system, and also ejecting large blobs of plasma. In the electric universe, these stars are deprived of electrons, which forces their outer plasma sheath to expand. A planetary nebula is not the remnants of a dying star, but instead are the structures that the star is connected to, which are being lit up in glow mode due to a pinching event which is taking place around the star itself. We know that what is termed as a young star can eject vast amounts of material from the jets, but this process also seems to happen with the larger, in quotes, dying stars. At the same time, we also see the formation of a ring system around new stars, which is often interpreted as an accretion disk from which planets may form. The same may also appear to happen with these supposed older stars, but now they call it a dust torus. In the electric universe, stars undergo a process whereby they become electrically stressed. There is an imbalance between the incoming charges and those flowing away. In order to deal with this, some of its charged material can be ejected. This can happen as a CME, or in extreme cases, large planet-sized chunks of plasma can be ejected. In the most extreme case, the star itself will split into two equal and sometimes unequal parts. There is much observational evidence to show that those latter cases occur right after a sudden flaring or brightening event. V Hydrae is what is called a carbon star. These are luminous red giant stars. These stars contain atmospheres where there is more carbon than oxygen. The two elements combine in the upper layers of the star, forming carbon monoxide. This leaves the carbon atoms free to form other carbon compounds, giving the star a sooty atmosphere and a strikingly ruby red appearance. This characteristic is not limited to massive stars, as dwarf stars are also known to be carbon stars. When astronomers developed the spectral classification of carbon stars, they had considerable difficulty when trying to correlate the spectra to the star's effective temperatures. The trouble was that the atmospheric carbon was hiding the absorption lines normally used as temperature indicators for the stars. Back in 1981, astronomers detected very fast outflows from this star. Recently, they have detected not just the jet-like flow, but that this flow consisted of compact plasma blobs ejected at high speeds, but also a slowly expanding set of 6 rings. The fact that they observed the star ejecting huge blobs of plasma on a very regular basis is not easily explained in the mainstream model, and would require a companion star which passed through the outer envelope of the star, pulling away material from the star and ejecting it outwards. The star is around 2,000 light-years away from us. Not only is it a carbon star, but it is a semi-regular variable star. It pulsates with a period of 530 days, and its brightness varies by about 1 to 2 magnitudes. On top of this, it also has another dimming cycle, which occurs every 6,160 days, and causes its brightness to drop below magnitude 12. This periodicity might suggest that there is a cyclic resonant circuit effect, complete with overtones. Through visible observations, they were able to determine that it might have a companion, but due to the large separation between the components, the physical connection of this pair is still considered provisional until sufficient radial velocity and proper motion data are available. This companion is also not responsible for the ejection of the plasma blobs. It is too far away for that to be the case. Recent data has suggested that the star might have yet another companion, much closer in. Direct observational evidence is hard to come by in these types of stars. They are large, very luminous stars which are surrounded by a dusty envelope. This makes it very difficult to detect nearby stellar companions. Some binaries have been inferred by radial velocity measurements. This method looks for a wobble in the motion of stars around a common centre of mass. This causes the star to sometimes move a little towards us and sometimes away from us, thereby altering its radial velocity. The problem with these larger stars is that they are believed to have strong variability intrinsic to their pulsating atmosphere. Instead, they turn to a technique called deep ultraviolet observations. Carbon stars are thought to be cool objects. The companions are likely a more normal star and therefore hotter. In their analysis, they determined that V Hydrae had the highest far ultraviolet flux. This they took as evidence of a companion, and they then linked this with the eruptions that they saw to determine it had a periodicity of 8.5 years. This is around half of the 6,160-day dimming cycle, so more likely the ejection mechanism is connected to the changes in the current from the cyclic resonance circuit effect. What if the UV excess was in fact evidence of something else going on in the star itself? That this process is what is causing the ejection of material and will eventually lead to the transformation of the entire surroundings. In the case of a super-red giant, we have a star which is electron deficient. It expands its outer envelope to increase the surface area for electron capture. The UV excess we see may be associated with the fact that the plasma sheath has expanded far enough, causing an increase in the electric field and hence giving the electrons a longer period of acceleration, whereby they collide with other neutral atoms, ionizing them, creating an avalanche process through more and more collisions. These types of stars struggle to deal with sudden electrical stressing, and the simplest way for them to deal with this is to discharge matter. Going back to our example of a young star with its outflows and the ring system, rather than considering them as young stars, maybe a better classification is a star undergoing extreme electrical stress. The same mechanism is what is causing all of these observations in V Hydrae. The way these stars manage sudden changes in electrical input is to discharge charged matter. This initially starts in the equatorial region, forming a torus or series of rings. As the toroidal magnetization builds, it may reach a critical point, after which an instability occurs. This switches its behavior to force it to start ejecting material out of the polar regions instead. These are the jets and the ejected material we see from these types of stars, and are also the same mechanism that drives the ejection from active galaxies. If we examine the rings, you might notice something rather interesting. The rings are not equally spaced, but it would appear that the rings further out are much further apart than those close by. If these rings were simply ejected material from the star, this material should slow down as it moves away from the star, and we would expect to see the rings get closer together as they move further away. The only reason that they will be getting further apart is if they are being accelerated away from the star. This would make sense if the star had a radial electric field driving away the plasma. A similar thing is also observed with the blobs of plasma ejected by the star. They initially appear to move at a steady speed, then suddenly underwent an acceleration. This star may well hold the clues to understanding the process that occurs when a star undergoes a sudden change in its incoming current, while at the same time being starved of a ready supply of electrons. The formation of both rings and jets is an indication of a star that is undergoing a significant change to its electrical load.